All right, welcome to Pre-Calculus, Unit 2, Modeling with Functions, Modeling Word Problems. This is part 2 of this video. So if you didn't watch part 1 yet, please watch it. We have already done 5 problems, and in this video, we're going to jump right into number 6. All right, these problems are pretty challenging. They get a little bit tough. Remember, the key things you got to be able to do is what formula do I need to use to solve this problem? And then how am I going to create a function that solves exactly what the question's asking? So let's dive into number 6 here. This is another really good one. It's actually very similar to the one we just did in the previous video, number 5. So consider a circle with the equation x squared plus y squared equals 16. That is a circle with a radius of 4 and its center is at 0, 0, as shown in the picture here. Now we're going to let point P be a point on the circle x comma y, right? So let point P be any point on the circle. So for example, this point right here, get any point, right? Any point, we'll just call it x comma y, any point. And then we're going to let point A be the point 6 comma 0. So there it is right there in red. There is the point 6 comma 0. Okay. Write the distance d from point P to point A as a function of the x-coordinate. So again, we want to create a formula for the distance that only contains x, because we want to write it as a formula for distance, and it needs to be a function of x, so no y's at all. So you do need to remember the distance formula, and remember the distance formula between 2 points is the square root of the x values subtracted. So you take your 2x values and subtract them, and square that. And then you take your 2y values and you subtract your 2y values and square that. So that is the distance form that I hope everybody knows. And if you didn't, well, you know it now. So here's what I want to do. I want to find the distance between a random point, x comma y, any point on this circle, x comma y, and the specific point, 6 comma 0. So let's start filling in the blanks. All right, so the x-coordinate here is x, so that's going to be x, minus the x-coordinate here is 6, and then that needs to be squared. Okay, well, that's pretty easy. Plus, now we're going to do the y-coordinate here, minus the y-coordinate here of 0, squared. Okay, so far so good. All right, so now distance equals the square root of, let's see here, so x minus 6 squared is going to be x squared minus 12x plus 36. I actually went and squared that out. Plus y minus 0 is y, and so y squared. Okay, but remember, I wanted a function for the distance that only contains the x-coordinate. Well, that means that this y value right here needs to change. Well, check this out. Look back up here. The formula for that circle is x squared plus y squared equals 16. So I know that this is a true formula, right? It's obviously the circle. So this means that y squared equals 16 minus x squared, right? All I did was a little bit of basic algebra there, subtracted the x squared over. So I could replace this y squared with 16 minus x squared. So now my distance formula is the square root of x squared minus 12x plus 36. And then I'm going to replace the y squared with 16 minus x squared. And that's it. Now I have a formula that contains nothing but x's. So all I'm going to do here is clean it up. The 1x squared here and the negative 1x squared here are going to make a 0x squared, so they could go away. And I have a negative 12x and 36 plus 16. If you need to grab a calculator, 36 plus 16 is 52. So there is a nice, fairly simple formula that contains only x. So, for example, if you give me this x-coordinate right here, which is negative 2, I have no idea exactly what the y-coordinate is, but anyway, the x-coordinate is negative 2. If I plug negative 2 into this equation, I will get the distance, the distance from that point all the way to this point, 6 comma 0. So let's actually do that real quick. So if I plug negative 2 in, so let's see here, the distance will be the square root of negative 12 times negative 2 is 24. 24 plus 52, grab a calculator if you need to. 24 plus 52 is 76. So the distance from this point right here, which has an x value negative 2, who cares about the y, because my formula doesn't have a y. The distance all the way to 6 comma 0, the distance is the square root of 76 which, if you're looking for an approximation, is 8.72. 8.72 units. All right, so that's pretty cool, right? It's a formula that can find any distance from any point on this purple circle to this point right here, 6, 0. All right, now they did ask me to do one more thing. It says to state the domain of the function. So the domain of the function is what values could x be, right? That's the input. The input is x. So what values can x right here be? Well, think about it. It's got to be a point on this circle. So the absolute lowest x value that we could be is -4, because you can't find a point further away than this one right here. There's not a point further away from 6, 0 than that point. So the lowest x value we could ever be is -4, and the closest point would be right here at +4. And every x between -4 and 4 would be any x that is on this circle. So that means the domain, which is what could the x coordinate be, would be any value from -4 to +4, or as an interval -4 to 4. Oh, brackets, because I could equal those values. I could be -4 or 4, because those would be the absolute furthest away and closest away. All right? So hopefully that domain thing made sense. I hope it makes sense. It should make sense. And you got to understand that I could maybe plug -6 into this function. But again, -6 isn't an x value from the circle. So that's why that would not be in the domain, because it's got to be on the circle, right? I mean, that's what x is. It's a point on that circle. So any x value from -4 to 4 would work. All right, so that's a pretty good problem. Hopefully that all made sense to you guys, and should be pretty easy. All right, let's take a look at number 7 here. All right. Rice is leaking through a hole in a storage bin at a constant rate of 4 cubic inches per minute. The rice forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. I'm going to write that down real quick. That might be important to note. The height equals the radius. Okay. If the cone is 1.5 feet tall now, how tall will it be in an hour? All right, so imagine we have rice and it's leaking from some position. It's falling. And as it falls, it creates a cone shape, right? That's the cone shape that it falls. And I know that the volume of that cone is 1/3 pi r squared h. But they did tell me that the height always remains equal to the radius. So that's kind of nice. That means that I could replace, well, I could actually do one of two things. I could replace r with h, or I could replace h with r. Now the question does ask about how tall it is, so tall is height. So I actually want h to be in my answer because I'm looking for height. So I'm going to replace r with h because, again, h and r are equal. Clearly said that. So 1/3 pi, if I replace r, but I can't talk today. If I replace r with h, that becomes h squared times h, which of course becomes 1/3 pi times h cubed. So here is my formula for the volume of this cone-shaped pile of rice. All right, so let's talk about right now. Right now, the cone is 1.5 feet tall. So that's 1.5 feet tall. Let's find the volume of the cone right now. If we were to pause time, no more rice could fall. Let's pause time. But hold on. One more thing I got to do. These are word problems, right? They're tricky. Notice that I am at some point going to have to take into account that the rice is falling at a rate of 4 cubic inches per minute. So that's in inches. So this is in feet. So I need this to also be in inches. That way my problem is all the same unit. So I can either convert the 4 cubic inches to feet, or I can convert my feet to inches. So I'm going to convert the feet to inches. So 1 foot is 12 inches. 1/2 foot is 6 inches. So 1.5 feet would be 18 inches. So the current volume of my cone is 1/3 times pi times the height of 18 inches cubed. All right, I'm going to go ahead and use my calculator to find that. I'm literally typing in 1/3 times pi times 18 cubed, and I get 6107.26. And that is cubic inches, inches cubed. Okay, that's the volume right now. All right, the question, though, asks me, how tall will it be in 1 hour? So I need to solve for height. So that means I need to find what's the volume going to be in 1 hour. Okay, this is where I really have to put my brain to this. The rice is falling at a rate of 4 cubic inches per minute. So every minute we're adding 4 more cubic inches to this volume. So in the course of 60 minutes, it's going to get 4 more cubic inches per minute. So 60 times 4. 60 times 4 is 240. So at the end of 60 minutes, there will be 240 more cubic inches added to this current volume. Sorry for that very bad circle. All right, so if I take 6107.26 and I add the 240 more cubic inches that's going to fall over the course of an hour, I get the volume. That's the new volume at the end of 1 hour. So now I just have to set that volume equal to the volume formula and solve for H. So the first thing I'm going to do is I'm going to take the 6107.26 plus 240, add that together. Then I'm going to multiply by 3, because the opposite of divide by 3 would be multiply by 3. And then I'm going to divide by pi. So I'm going to take 6107.26. I'm going to add the 240. I'm going to multiply all of that by 3 to get rid of that 1/3. And then I'm going to divide all that by pi, and that equals h cubed. And then now to get rid of a cube, I'm going to use a cube root, or a cube root is the same thing as a 1/3 power. So to solve for my height, I'm now going to go to my calculator. I'm going to do all this one step at a time. 6107.26. I'm going to add the 240. That's my new volume. 6,347.26. I'm going to times that by 3. Then I'm going to divide that by pi. And now I got to take the cube root of that, or I could raise it to the 1/3 power. So taking that value, raising it to the 1/3 power, gives me an H of 18.23. And that would be in inches. Remember, I did convert everything to inches. So 18.23 inches. So we started at 18 inches. And then after an hour of rice falling, I added some more volume to that. And remember, when that rice falls, it's going to slowly increase both the radius and the height. And the new height of that cone, after some new rice has fallen on it, is 18.23 inches. So pretty good problem. Sorry, it's a little bit messy there, and it kind of looks like it's holiday themed with the red and the green. But we all see that it's all started with the volume formula, knowing first that I can replace R with H because it says the height and the radius are equal. Then finding my current volume with a height of 18 inches, 1.5 feet. And then I said, well, over the course of an hour, it's going to grow by 240 inches cubed. So what's my new volume? And then I set that new volume equal to the volume formula, and I was able to solve for the new height. Pretty good problem. Hope you guys understand it. Really like that problem. All right, number 8. This is another classic calculus type problem. An open box is made by taking a flat piece of cardboard that measures 6 inches by 8 inches and cutting out a square of side length from each corner. Maybe drawing a picture would help. So I got a rectangular piece of cardboard here. It measures 6 by 8. Sorry if it doesn't really look to scale. And I'm going to cut out a piece from each corner. And that piece measures x by x. So x by x. X by x from each corner. And once I cut that out, imagine that I could now fold up the sides and I could create, well, this is a terrible drawing. I could create a, I got to redo that. That's just absolutely terrible. Again, you got to imagine if I fold up these edges, I'm going to create a box. Slightly better. Okay, now it says, write the volume of the box as a function of x and state the domain. Okay, well, let's see here. So volume of a box is length times width times height. Okay, but that's 3 variables. I need all x's. So let's see here. So the side that was 6, I'm going to take out x from each side. So that is now 6 minus 2x. The length, which was originally 8, but again, I cut out x from each side, is now 8 minus 2x. And the x is what I cut out now gets folded up, so the height of my box is now x. So the formula for my volume would be the length or width, depending how you turn the box, 6 minus 2x, times the width or the length, again, depending how you look at the box, 8 minus 2x, all times the height of the box, x. Look at that. That's it. There is a formula for the volume based on x. Now, if you really wanted to, you could go ahead and multiply this out. I mean, you don't have to do this, but you could. So if you multiply this out, we get 48 minus 28x plus 4x squared. And then I got to multiply all that by x. So I get 48x minus 28x squared plus 4x cubed. I did not have to do that. This final answer right here would be good enough for me. But if you do multiply it out, you get, another similar looking formula, but, just multiply it out. So that's a formula for the volume of the box written as a function of only x. Now, what about the domain? Now, we have to think here, right? If you look at the shortest side is x. And if I were to cut out 3 inches from each side, that's 3 this way, 3 this way, I would literally be cutting the piece of paper in half. And if I cut it in half, then I can't even make a box. So the absolute smallest, the absolute biggest amount that I could cut out would be anything up to 3, right? Like 2.99999. Imagine if I cut out 2.99999 from each corner, I would fold it up and have this very, very tall but super skinny box. Okay, great. So the most I could cut out is 3. I cannot cut out any more. If I cut out 4, then I'm not cutting out squares, because if I cut out 4 this way, then there's not even enough to cut out 4 that way. So 3 is the most. And the lowest, the smallest amount I could cut out, which would be anything right above 0, because I have to cut out something. So even if I cut out 0.01, a very, very teeny amount, then I would have a very, very wide box that's very, very, very short. So again, the domain would basically be 0 to 3, okay? Or x has to be somewhere between 0 and 3. Okay, it cannot equal 0, because if I cut out 0, then I have a flat piece of paper. It's not even a box at that point. If I cut out exactly 3, I'm literally cutting the box or the piece of cardboard in half. So that's not going to work either. So that's why I have to use parentheses. So anywhere from 0 to 3 there would be the domain. All right, now it says to graph the function to find the maximum volume. So this is, again, let's put everything we've been learning the last couple units together. I could go to Desmos right now and just type in this formula. V equals 48x minus 28x squared plus 48x cubed. I'd actually recommend doing that. But there's no point in looking at the entire function, because the only part of the function that logistically makes sense in the real world would be 0 to 3. So after you type this into Desmos, you could use the squiggly brackets and type in 0 less than x less than 3 and close the squiggly bracket. And then what you could do is you would only see the part that makes sense. And voila, here that is. So notice that the graph is only graphed from 0 to 3. Everywhere else doesn't even make logical sense for this real world problem. And this is a formula for the volume. So x is how much I'm cutting out. Again, 0 inches all the way to 3 inches. And the height would represent the volume. That's the y coordinate, right? So all you're going to do in Desmos is click on that maximum value right there. That's all I did. So I get a volume. The maximum volume would be 24.258. That would be inches cubed. And how much I would have to cut out for that maximum volume is 1.131 inches. So if I cut out 1.131 inches from each corner of this cardboard and fold it up, I would create a box that has a maximum volume of 24.258. Now again, that's why I needed the max. If I were to grab this value right here, that would be an x value of roughly 2.5, but it would not contain a maximum volume. The volume would be right around 10 cubic inches. Well, I don't want 10 cubic inches. I want the maximum cubic inches. And that is, again, finding that maximum value right there. So it's really cool when you just plug in the Desmos and then, again, restrict your function to the domain that makes sense. Again, you can't cut out a negative amount of corners. So no negative numbers even make any sense realistically. And I can't cut out more than 3 because the shortest side is only 6. So if I cut out 3, I'm cutting it in half. So that wouldn't make sense either. So pretty cool problem. I think that's actually a pretty easy one to understand. We needed to find a volume in terms of x. how much we cut out from each corner. And then again, if we make a graph of my volume function, I could actually see what the maximum volume would be and how much I would need to cut out to produce that maximum volume. So a couple really good problems in this video. I think each one of these is kind of a top tier problem in terms of difficulty level, but hopefully they all made sense. And now it's really up to you guys to just practice some more examples similar to these. That way you could really prepare and get better at these problems. Because I'm going to tell you, they're not easy. They do take a little bit of time to figure out. All right, best of luck. Hopefully they all made sense. Obviously, talk to me if you need to.